Hello, this is a quick tutorial about ISE Project Navigator where we do FPGA design for NEXYS Digital System Builder board from DIGILENT. This is a Xilinx FPGA on it built-in and some extra stuff like switches, diodes. This one is a legacy board, it's not the newest one, and but it's still okay. You can still buy those somewhere on the like eBay places. Some of the used or never used boards, so they are still available and still quite nice and powerful boards. So welcome here. To start with, we need a general PDF about it. So this is like a reference manual or a quick start manual, anything like that. That will list all the stuff which is on this board, how to set up the jumpers and stuff. And we are staying somewhere here around the LED switches and 7-segment display. And in this case, we use SW0 and SW1 to produce output to LED1 or LED0 maybe. This is going to be a small AND gate where we do manipulate SW0 and SW1 to produce something on the output. And this is a close look at the the main chip located on the board, XC3S1000 board FPGA, which will be needed for future reference when we do the setup on the ISE Project Navigator. This software is installed on top of VirtualBox, which is virtual machine from Oracle, and it doesn't work on Windows 11. You need to have a Windows 10 or lower system. I don't know, there is some incompatibilities in the system and recognizing the installation files. I don't know. There's plenty of YouTube videos how to do the installation, so please follow those. You can find plenty how to perform that stuff. The other question is why? Why such a thing with such a hurdles? The newer software, which is Xilinx Vivado, doesn't cover or doesn't support the Spartan 3 device which is installed on this board. So that's why I had to go and install this free software. It's ISE. You can look at it on the Xilinx website. It is available to download for free, install for free, and it works with most of the functionalities for free. Also, the same comes with the VirtualBox, which is the virtual machine from Oracle that does also support the system, and it's installing without any problems. So if you want to try it, I recommend it too, because testing this stuff on the empty, it's not very nice. So I have it done on real life, and you will have the in-hand experience with touching it, trying to program it and using it, which is very, very recommended. And in this case, you learn most. If you find something which is not covered here, I recommend to go to the website, Google or Stack Overflow, find the dropped errors, warnings, and you can solve the problems by yourself. If not, drop them comment here. Let's start our project. So we go for new project, and then let's give it a name and gate. That top level stays HDL. Now we need to fill up the boxes. First one is Spartan 3. That's XC3's Spartan 3 family. So the rest can be taken from the chip itself. That's the photograph of it from close. So XC3 was S1000, and the package is FT256. I found found this number on the package. So this thing goes into the project manager. Oh, Philip up there. That is just specifics of the outputs or the pins description, which is important for our physical connections. FT256. The other speed and LC for simulation stays as it is by default. We've got a little summary here, and then we can press finish, and after a moment we'll have general things for that. We select new source to describe the behavior of what's happening there, and we select VHDL module. We need to give it a name as well, so I'm just tending to give it the same name just to keep it consistency. And we need to select what inputs and outputs we want. So that's two inputs, switch 1 or SW0, SW1, and that's two inputs, and LED to be showing us what's the output of our action is going to be. And next, and finish. After a moment, we've got like a frame for our program, our script. We're going to fill between begin and end, just to present what we're going to produce. And what we're doing there, LED as an output, and what we assign to LED is the result of operation of switch 1 and switch 2. It's like logic operation, switch 1 and switch 0, SW1 and SW0. And this AND is represented by the same thing as the logic gate AND. So if we type it in Google or any search engine, it will show us the behavior of that gate. And it's very simple. The gate symbol is 0, is A. The inputs are A and B, output is Q, and this one is cheating to us. Oh, it's not showing us 1, 1, what is going to be when two inputs are ones, so the little board or little grid is not fully filled up. AI overview made us not much smarter. Anyway, that's the one. So two zeros, if any input is 0, the output is 0. Only when two ones are present as inputs, then we've got 1 on output. So if we're going to switch our switches, then we will observe 1 only when two of those things are going to be ones. And this is represented in this little logic which is written. Now, the SW0, SW1 and LED signals are just logical thing or higher level of abstraction, and we need to connect those signals to the real world entities. So what we want to do is to transfer those or connect to, say, somehow between the abstract of the SW or the names SW1, SW0 to the chip. So we've got that little additional file which will show at the ports names are like L14 and 15 or J16 here to be pointing the software how to synthesize the file, so how to bring the outside world pins to the thing. So now to do it, we need to add a constraint file So this is implementation constraints file, which will tell which location or which pins are connected to which signals. So to do it, we do a new file, we call it and pins, and now we need to specify particular signals and their location. So we select net, which is there in the other file, and then SW0, and then we tell it which location does it has and the pin. So location equals, and then we need to look at this little PDF which does say the pin numbers. Either this one or schematic, full schematic will also tell where to connect. So this is switch 0. Now we go for switch 1, and also finding the location of this pin, or where the schematic defines or tells us where is it connected. And we've got the last one, the output LED, to specify where it goes. Again, and then let's quickly check, is it still L14 and 15 J16, and saving that. Now we can do the synthesis of the initial files by just clicking twice into proper place. It does take a while though, and that's probably one of the things which is not very nice in the synthesis of FPGA. It takes time. Sometimes compilation of the equivalent program on the processors lasts quicker, but in this case it did it nicely for us. There is a chance we can quickly observe what happened as a result of the synthesis of this file in the shape of schematic. If this, because this one is quite simple, we can probably observe the gate being presented after the synthesis. So now it's just, this is the representation of our program. We can zoom in by clicking the inside, and here it is, AND gate with two inputs, SW0, SW1, and output as LED. So you can probably remember this one from a couple minutes ago. AND gate symbol, inputs and outputs. That's the result of our program. Okay, we can do a simulation by adding a new file, and this is called testbench, where in this file we name it TB as testbench. In this file we can define all states which are going to be given to the inputs, and then we can observe the outputs on the corresponding screen, or a little plot which will show how does it work. Now we delete this line because it says about the clock. We're not using the clock here because this is like a pure computer combinational logic, so it doesn't, the state of the previous or the future states doesn't depend on the clock or clock cycles. So what we've got, we need to go between begin and end process, where we say about our states of the switches. So we've got switch 0 given 0, and then switch 1 given 0 again. So we want to go through all states, and because this our project is relatively simple. We just go through all four. So we will have 0, 0, 0, 1, 1, 0, and 1, 1 to see how the states influence the input states, influence the output state. And then that's like our scenario where we precisely describe all the states, and we wait some time just to have a chance to observe the changes on the kind of scope. You will see that in a second. So that's our scenario. We press save, and then we can switch to simulation here, and then go for behavioral model by clicking twice this one. It will go and show us this one. It's not showing like properly, and it's only because we are zoomed in to the last bit of the simulation. When we press this button, we zoom into such a way that we can observe whole state, and this is it. We need to bring the cursor somewhere here. The cursor is showing the current position, or the cursor position of the values SW0, SW1, and LED. And so you can see that zeros, and then when we can move to another state of the simulation. So this is after 200 nanoseconds. We do have 0, 1, and output 0, and then the last bit is the 2 ones, which bring LED to 1. So this is the quick simulation, and this tool is in FPGA design is very important, because very often whatever we expect is not happening, and after this simulation stages we can quickly validate or see if any inputs or any behavior is as we want. So is expected as output is the one we expect, or is it something we mistakenly happened? So that's our simulation. Very helpful tool to observe and see. And now we can get into the programming of the device. So we click twice on the generate programming file, and the moment later the ISE project navigator will spit out bit file. A bit file is used to program the FPGA, and there is two modes we can have it programmed. We can have it programmed as is and only to the FPGA program. And to sort it out, we've got two startup options. This is how going to behave the FPGA after on the start. So it's either going to use a clock coming from the FPGA itself or from JTAG, and depending on that we are going to generate or have two behaviors. Either we can start just after the programming and JTAG will provide the clock to run the program or to start the program, or we can have it generated from CCLK clock. So this will do the startup of the FPGA by generated clock from FPGA, and this is when we load the program from the PROM, a small chip which is located on the board, which will consist of all generated files or the bit stream to run the program. So we can, I'm generating two JTAG with JTAG clock and with the CCLK clock just to show the behaviors. We're using Adept. The Adept is a little software provided by DIGILENT to connect the board through the USB port, and in this case we can recognize the board and we can select the files to be programmed. If we try to program FPGA itself, we need to use JTAG clock. This one will show setup clock is invalid. This one causes the equipment to not to start. You can program it with this, but it won't work. So instead of that, we can select the corresponding file with the and that will gives us a warning again, but the program is not working. So it's waiting for different clock to start up. So instead of that, we select program with the JTAG clock. This one does the program without any problems, without any warnings, but the program or the file is going to be lost when we do power up or power down and power up. That's going to be lost. So if we program PROM XCF04, then this one provides us like a more permanent programming, and that keeps the stuff inside for possible power cycles. To program the PROM, we need to select programming file. It can be the same with but with not JTAG clock, but we need to select it with CCLK clock, because this is the clock generated instead of FPGA, and that will clock the PROM to load the whatever is consisted in the bit stream to the FPGA on the startup. So we programming PROM, not the FPGA by itself, and then we need the one with the option selected CCLK. So we program that one. Wait a while. Sometimes this PROM programming takes a little bit longer than programming FPGA itself. Anyway, it's the permanent one. If we power up, power down, it's just the thing that you need to remember, that in our board, the Nexys board, you need to change the settings of one of the configuration jumpers. This one has to be selected for flash, and then every power up, power down is not like as permanently removes the consistency of the PROM. It will be loaded every time. So we're using impact here, but impact has to be used only in the case we have different programming cable, like USB from Xilinx platform cable. In this case, when we've got that port connected only with the USB on the provided USB port, there is a problem with recognizing it. So that's the platform cable USB we need to use to program directly from ISE. Otherwise, we cannot find the cable, it cannot be recognized. I don't know, maybe it's lack of some of the drivers, but generally it's very hard to program it just like that, unless somebody knows the solution for that. Board, it's ready to be programmed. So, and it is programmed on the PROM, but not on JTAG. As you can see, there is like a tiny PROM. It's here, XC4. And then this one is programmed, but because this little jumper is set up to JTAG, now it loads anything from JTAG, and after power up, power off, it's the contents is deleted. So now we change it for flash to provide the possibility to load the program from flash, and then little dawn says that it's been successfully, the FPGA has been successfully loaded from the PROM, and this is the action SW0 and SW1. This is the switches we programmed to be like 1 1 gives 1, and you can see it on the D0 LED, which states the shows the state of the gate output. So we've got 0 1 1 1 1 0 1 1 and 0 1. So of course it's working as we expected and as we wanted. When we power it off and on, we still have it programmed, and then action and all behavior is kept. And when we change the jumper to JTAG, and the content of the file in this case has been kept. I don't know why. It's probably the capacitor hasn't been discharged or anything like that, but after longer power off, we should lost all stuff which has been sitting. Yes, and it's clean. You can see it's not showing off anything. No action programmed last time. So let's try again, and yes, empty, clean. So to have it back to our previous position, we can change again power off, change the jumper to flash, and power on. In this case, it can be kept all the time. So if you want anything of your FPGA design to be kept, you need to program that into the local PROM. Some of the FPGAs, not this one, has its own memory for storage of the program, so it can be done, but it's very rare. Generally, a little PROM is kept from outside. This one has been programmed now by JTAG, so I managed to program it again, but as I said, after power off and keeping the JTAG only, that program is going to be lost from FPGA. And that's it. That's all the story for now. I hope you liked it. At least it was hopefully clear enough. Excuse my not perfect quality and me not being very fluent. Anyway, that's one of my first videos, so excuse my faults. I hope and I aim to be better. So maybe next one will be much fluent and fluid for you, not to be stopping, having plenty of breaks and empty quiet spaces in the videos. So please comment if you like, put a little thumb up, thumb down, well, if needed. Subscribe, I'm not sure if you like, yes, please do, but and then wait for another one. I hope you will have some real life use of these videos. Maybe in some next future episodes, so we try to program 7 segment display which is present on this board, so that should be easy enough, and it will be a little bit more complicated, but still simple for the beginners not to be distracted or being dragged into some massive details. All right, bye, thanks.